Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 11, Multithreading, coming from the previous episode where we talked about smart pointers. Threading is fairly easy to use in Rust because all you have to do is use the standard libraries thread spawn and pass it a closure, and well, then you already have your thread going. This will then use all CPU cores available. And this is much better than Python because there you have the global interpreter lock. So you can actually use threads, yes, but they will still only consume one CPU core at max because of how the global interpreter lock is implemented right now. The Rust compiler makes it kind of hard to introduce concurrency problems into your code. So it should actually help you a lot to figure out, oh, this does not work this way. I have to be smarter about how I pass along all my data and share it with the other threads. There are lots of useful crates that exist already in the Rust environment. So you can have Rayon that will basically automatically for you distribute the workload of your algorithm to multiple cores. In Parking Lot, you have more powerful locking structs, for example, constructs for your multi-threading. Crossbeam is a good library for all kinds of things multi-threading, but especially Crossbeam channel is a very widely used message passing system between the threads to keep each other's updated or share information. And easy to use is also thread pool. So if you want to constrict the maximum amount of threads that do the work that you want to do, you might consider using this crate. Now let's hop over to a minimal example in both languages. On the left, Python, as always, here we have to import the threading. In Rust, this is not really necessary because if we just use the full namespace qualification, we can just use it directly. Then we define a function that we gave also an argument that's called a name. All we do is we use our global data 100,000 times, update the data by adding 1 to it. Now, below here, we initialize data with 0. This is holding our handles of the threads that are created. Then we start 10 threads. This means we get threading to use the thread class. The target is our function that we created up here. And the arguments is the index that we get of our range. So in theory, the name of our thread is the number of the thread that we created. Then we append this to our list to have the handle that is returned, or well, the object, which is a handle to the thread that is returned from threading thread. And this is needed because down here we have to join for the threads, meaning waiting for each of those computations. So 100,000 times adding 1 to be completed. And at the end, we print data. Now, the same naive approach we can do in Rust. On the right side, we just get ourselves a U32 with the value 0. Then we also have our thread handles in a now empty vector. We create our 10 threads. We directly use a closure to do this. This means our standard thread spawn has a closure that runs 100,000 times the addition. Here we also inside the closure print the data after our math is done. We push the handle that comes from our spawn to our vector with the handles in order to join. So this stays the very same as we have on the left, with the only difference that we, in the error case, unwrap to create a panic because we didn't handle whatever error the join caused. And at the very end, we try to print data, and we expect, since this is 100,000 times, 10 times, to get data to be the number of 1 million. Well, let's run the code. On the left, we can run the Python code. So let's do this. We can actually run python 3 naive count.py, and we get 700,000 something as the result. That's not a million. Now it's closer, much closer to 1 million, but still not a million. So clearly this is broken. Let's see what Rust does. So the Rust compiler will compile the naive count, I assume. It does. And we can run. That's not how it works. We have to do this. We can run naive count, and we get actually the output of 100,000 very often. But then the final output is 0. So what's up with that? Okay, so we should probably swap to our Rust panel and run again the naive count to now analyze the code of what's going on in Rust. Now, we get 100,000 as an output. So clearly each individual closure actually does the work. So there is data that starts at 0 and gets counted up to 100,000. So that works fine. Since here we have the output, this is proven. Now, one keyword I jumped over before explaining the code is this move keyword. So what does move do? It would move the current scopes variables that you use in your closure into the closure. Now, data is a U32. Now, a U32 is a very primitive data type. It is easy to copy, and in fact, there is copy implemented. Now, move will copy for you this data type, meaning that in each individual thread here gets its own private data variable, and it increases it, and this is safe. This is why the Rust compiler did not complain to us. This is why this works, but it does not work in the way that we intended to, because we wanted to increase this global, if you want, data. But we didn't do that because this data actually is never touched. Hence the output at the bottom here will be 0 because each thread is having its own private version of data that it increases. Now, what would be the easiest approach in Rust? Well, we should get a mutable reference and pass this into the thread, right? Now let's try that and see what happens. We hop over to the code. We have our data here and our loop. Now for each thread, we want to have a mutable reference. So in theory, we could go like let d equals mutable reference to data. And in here, we do this. Save that. Clear rust c naive count.rs. Now the compiler is really not happy with us, and the reason is fairly clear because we create 10 threads, right? So if we borrow the data here, then afterwards we try to print it, this will not work. Now we can get rid of the print statement and see if this makes it compile. Let's see. And no, it does not. It still complains, but this time about the very last print statement, because this is an immutable borrow, but we handed out multiple mutable borrows. And here it also tells us that we did it in the previous iteration. So clearly this mutable borrowing, that's not the way to go. But we remember from our broken Python code, but there we used a global variable to increase in every thread. To increment in every thread, we use the global variable in Python. Now let's hack this into our Rust code. Now there is no concept of global variables in Rust, but we can have static variables. So there, the known location on the stack is not changed in the code ever. This means the whole code knows exactly where to go. So this is basically what we would consider a global variable. Let's try that. So this clearly doesn't work. I will change this back to being data, because we will use a global variable. We can remove this one. We change the let to be static mute data u32. So in theory, since we have this as a static address, it's mutable. This should work. Let's see what the compiler lets us know about that. I forgot to... Let's get rid of this statement actually. So now the compiler tells us, well, use of mutable static is unsafe and requires unsafe function or function block. Well, let's do that. We cannot make main unsafe, but we can make a huge unsafe block inside our main. So let's do that, because all of the code needs to have access to this static data. So once we have that figured out, we can run the Rust compiler again. Now it warns us that our static variable is not in all caps, but that's fine. We have written code that compiles. Let's run it. And we don't get 1,000,000. Second try, not even close. Random numbers, as we have in Python. So clearly this is broken. We have to improve this. Now, the correct solution, as people that have already coded with multi-threading code, is to use locks. Now this naive count is not a good idea. The reason is all those threads in parallel access the same amount of data. Everyone reads a different value, and this is not happening in an orderly fashion. Now the least performing, but at least making it correct version of a lock would be the lock count that I've implemented in Python in this way and in Rust in this way. On the left, what we've changed in the code is we added a second global variable called lock. And this is then simply a threading lock that you can create. If you want to hold the lock, we can use this context handler, so with lock, and we get our loop that does the increment. What is then actually happening here is we start those 10 threads, but one thread after another will wait for the lock to be freed, does his math, so in our case the simple count up. And basically we no longer have parallel computation here, because every thread will run after the next one to do the computation, but at least we have now the correct output. So if we run this version of the Python code, we should see that lock count becomes 1,000,000 and it is correct. The same we can do for the Rust code. Let's hop over quickly to also the Rust shell. We have to import the sync libraries ARC, so atomic reference counted pointer, and mutex. There's also other locking structs that you can use, like a read-write lock, for example, and many more. Especially for a counter like this, you might want to use an atomic integer that will be much, much faster and more efficient. So for the generic use though, we would then create our ARC with the mutex inside, and in here we would have our value that we want to increment. So now data is actually this wrapper to our value x that we initialized with 0. We still keep the same code with the vector and the creating of the 10 threads. But here is the big difference. We clone our data ARC, and then the my data moves into the closure that is the spawned thread. So in order to access the X, now we have to use the lock of the mutex. Unwrap, if there is a problem locking, we would then panic out. But we can expect the lock to work, so unwrapping is fine, more or less. Then we get our mutable reference to our data inside the lock. We can loop the 100,000 times, dereference it, add the 1. We add the handles to our list, join them, and here, in order to read what we have changed, we have to also acquire a lock of again and dereference it to get our value that we have inside our data. This now works correctly, but has the same problem. You are acquiring the lock, doing the math. This will then actually end up being a serial process, but at least the math you're doing is correct. So if we do the lock count example, we will get the correct value of 1,000,000. The tries we did before in the Rust code have shown you that the compiler will keep you from shooting yourself in the foot, because you will have to use unsafe code to get this undefined behavior where random counts will be produced. In order to get your multi-threading code working in a meaningful way, the compiler will actually force you to use reference counting and locking structures or other intelligent features like atomic integers. Now let's use a more complicated thing. So here we do something that can actually be done only with atomic ints. We should maybe use a more complicated object. This I have prepared as well. So we have lock object code. There's not much that's changed here. So all I had to do is change the x to be a vector. The rest, wrapping all of this stays the same. And in here, we increment the first value that we find by 1. And the thing is happy. So that's the advantage of using those amazing smart pointers for multithreading and the locks that exist. Now let's see if this one works. So we rust compile lock object.rs and we run lock object.rs, and it does work greatly. If we go back to our naive count, if we were, so we're back at our naive count example. If I remove the unsafe block again, and we change our data to be the vector, so let's do it this way so we can keep our old so we have our vector with 2 zeros, and in here we want to do the same as we did without all the clever locking and reference counting. We will have to fight the compiler, because what we have to change, of course, is the display, because it needs a debug output. So if we compile that, we have to fight the compiler, because now it no longer simply compiles as we had before, where we didn't get our desired result because it printed 0 at the end, but it also no longer just stays quiet compiling, because now the move becomes a problem, because the data is of vec, which does not implement the copy trait. So before, this primitive that we had, the U32, was easily moved inside here and became an internal variable only to this thread, because a primitive can be easily copied and has virtually no performance problem. But a deep copy would be an issue, therefore it's not by default implemented for vec. You would have to explicitly call that. And just moving it in more than once, so for all of our 10 threads, does not work with the borrow checker model of the Rust compiler. So it immediately lets you know that this does not work and forces you to find out how the locking works. So basically the Rust compiler forces you to write correctly working concurrent code, which is not the case in Python, but Python is just the example in this course where I'm going from Python to Rust. This is true for many other languages, so there will be no warnings put out for doing an increment on a global variable in C either, or in Go for that matter, and many other languages. Therefore, I highly enjoy writing concurrent code with Rust, because the compiler will immediately hit me on my fingers when I'm doing stupid stuff, and I learn a lot really fast by reading the error messages, and of course by designing my code right away. Thanks for watching. Coming up next on the From Python to Rust series will be modules.